Okay, now let's talk about the second type of memory device, which is called flip-flops. And the most basic one is called D-flip-flops. This kind of corresponding to the D latches. But the main difference between a latch and a flip-flop is that the flip-flop is an edge-triggered circuit, while the latch is level sensitive. Level sensitive means like the output of the latch can only change when the enable input is in its active level. If you remember the gated D latch, right, the output can only change when the enable equal to 1. Okay, but an edge triggered means the output can only change when it detects certain edge, and the edge is where the signal level changes. For example, if we have the clock input in the flip-flop, when it changes from 0 to 1, there will be an edge, and you will call this rising edge or positive edge. When you change from 1 back to 0, we have a falling edge or negative edge. So that's the meaning of edge. And talking about clock basically just the enable input for flip-flops. Okay, but it's special in those places. Like first unit it's periodic. When we talk about clock, it's periodic, but the enable it doesn't need to be periodic. Okay, and in most cases, at least here, when we talk about it, the clock signal has 50% duty cycle, which means half of the time in the period, the value of the clock signal is 0, and the other half, its value is 1. Okay, and finally, the clock signal allows the FF to change states on its rising and falling edge. We'll talk about this. So to give you an example, this is edge-triggered D flip-flop. So if you compare this with the D latch, you will find this part basically is the D latch. But we add a pulse transition detector circuit here. So this circuit will detect when the value of the clock signal changes. Like in this case, we say we only want to detect the rising edge, right? So whenever the clock changes from 0 to 1, this circuit will detect that, and then it will output a very short pulse, like this. Because we know that when basically this is the enable input for the D latch. When enable equal to 1, this D latch will work. The output can follow the input D, right? So basically just this circuit just generates a very short pulse here where we have a 1. Then this will work for a very short period of time. Then it will go back to the low change state. So if you remember the truth table for the D latch, so we have the enable, we have Q and plus 1 the output, right? And we have D input, but we don't have to include it here. So if enable equal to 0, we know the latch is in its no change state. So which means Qn plus 1 just equal to Qn. So no change. However, if enable equal to 1, then Qn plus 1 will follow the value of D. And if D equal to 0, that's reset. If D equal to 1, that's set. Right? But now we have this edge or transition detector circuit here, and it will detect the rising edge of this clock signal, and then you can change the output. And so we can, but before we talk about the truth table, let's look at this symbol, circuit symbol. It looks like this. The only difference is that we change the enable input to clock, and we put this arrow sign here. This arrow sign basically tell you that this device is a rising edge device. Okay, rising edge, which means the Q can only change value when we have a rising edge at the clock. Right? Then it's easy to write the truth table. So we have the clock input, we still have D input and Q and plus 1. Okay, when clock equal to 0, it's not an edge, right? So Q and plus will not change. It is still equal to the original state. If clock equal to 1, still not edge, no change. If it's a falling edge, still no change, because this is a rising edge circuit. Only when we detect a clock rising edge, then Q n plus 1 will follow D. If D is 0, we got reset. If D is 1, we got set. So that's the truth table for D flip-flop. And one more time, the main difference is that it's edge triggered. There is benefit using edge trigger than the level sensitive circuit. We will talk this later. Just like the latches, it's very important to understand how to read or generate the timing diagram for the flip-flops. Okay, first let's rewrite the truth table, or sometimes it's called state transition excitation table. Okay, for the D flip-flop. So we have the clock input, we have D input, we have Qn plus 1, and then we have Qn plus 1 bar. Okay, so if you remember, if it's equal to 0 or 1, right? It doesn't matter what happened to D, the Qn plus just equal to Qn, so this will equal to Qn bar. Okay. If the clock signal equal to, actually we can include the falling edge here. In this case, we're just talking about, just for example, let's say we are talking about rising edge flip-flop. Okay, so we can include the falling edge here because nothing gonna change at the falling edge. So only when the clock is at rising edge, if D equal to 0, the Qn plus 1 basically will follow D. So Q bar will be 1. Also, if at the rising edge, if D equal to 1, Qn plus 1 will follow D. This will be 0. Okay, once we have this table ready, we can understand the timing diagram. In this diagram, yeah, I already give you the result, so we just look at why it looks like that. Okay, so starting from the first clock cycle, cycle 1, let's say D value is 0 and Q value is also 0. Okay, this is Q bar basically. So you can, according to the table, we know that in this period there is no rising edge happens. So Q value will not change. It keep 0 until we detect a rising edge here. Okay. Then at this rising edge, we know Q needs to follow D. At this rising edge, we need to check the value of D. But we need to check before this edge. Okay, don't check after. Okay, check at this point. Check the point right before this time point. Remember, this is T. Okay, the x-axis is T. So it's 1. That's why the Q will change to 1 here. Okay, then at this period, no more rising edge, so Q will not change. You will keep at 1 until the next rising edge, and at this edge, the D value is 0, right before this edge. Okay, then Q will change back to 0, and then it will keep 0 for a while until we see another edge. So like that's why I talk about you need to check the D value right before that edge. So like sometimes you will see this happen. What will happen if the D value changes at the same time as the edge comes? So we're always using the value right before the edge. Okay, because this is realistic, because in real circuit there's some time delay for the signal to transfer from D to the output. Okay, so if we consider that, we always look the point right before that edge, because that point, that value will determine your output, not the value after that. Okay, so in this case, we will take 1 as the d value. Then your q has to change to 1. Okay, then you keep 1 till next edge. At the next edge, d change value, but before that edge, we know d is 0, so q has to change to 0. Okay, then till the next cycle, okay, another edge, rising edge shows up. Now d is 1, so q has to be changed to 1. Okay, then it will keep the same for this period. Then we got the 7th rising edge coming, and the d value is 0, so q will become 0. Now at the 8th edge, d is 1, so q has to change to 1. And at the 9th edge, it's 1 here, so that's 1. At 10th edge, d is still 1, so q is still 1. So now you can understand why we get the waveform for q like that. And q bar basically just the opposite of q. And probably you noticed another thing, that in the flip-flop we don't have the forbidden state or no use state, right? Even though for D latch it still doesn't have those states, but later on we will see that in the other kind of flip-flop we don't have to worry about the no use state anymore. So that's one advantage of using flip-flops. Okay. Now let's look at the falling edge D flip-flop. To make a flip-flop D falling edge, all we have to do in the symbol is just add a bubble before that arrow sign. It becomes falling edge. So this time your output can only change at the falling edge. So first let's mark the falling edge in this clock signal. That's a falling. Falling means change from 1 to 0. Okay. So actually we can ignore those lines, but we add this new lines. So how do we figure out the q value this time? Let's say q still start from 0. So at the first edge, falling edge here, d is 0. So q will be 0. Even though d changed to 1 here, but because there is no clock edge coming, so the q value won't change. Okay, until the next falling edge, now d is 1, so q has to change to 1. Okay, then it will keep the same until the next edge, d is 0, then q will change back to 0. Then wait until next edge, we still got 0, so q is still 0. At the next edge, d equal to 1 here, so q has to change to 1. And keep 1 for a while until next edge coming. And here d is 1, so q is also 1. So that's how we figure out the output. Okay, now let's look at some other flip-flops. JK flip-flop. JK flip-flop in many ways is similar to the, if you remember, the RS latch. Okay, but it's a flip-flop, so it's edge trigger device. You can treat J as a set input, K as R input. This will help you to remember the truth table or state excitation table, whatever you call it. Okay. So for JK flip-flop, if the clock, in this case we can tell it's a rising edge one. It also has the falling edge version, but here we start with rising edge. So if the clock is not at rising edge, basically it includes 0, 1, falling edge, right? Those three different cases. In those cases, it doesn't matter what value you put J and K, the circuit won't work. Won't work means the output always follows its previous. So you can, yeah, the truth table is copied. So Q0 here basically means Qn, so the current state. Okay. when the clock is at its rising edge, if we detect the rising edge, and now the output can be changed. So if JK is 0, 0, we still have the no change state. Okay, 0, 1, this is, you can see this is like a reset. So output will be reset to 0. 1, 0 is like set. Okay, and the 1, 1, this is special. Remember I just told you in previous slides, like in flip-flop, we don't have to worry about the forbidden state. Okay, so 1, 1, actually what will happen to JK flip-flops is that the output will be inverted, so equal to the current state of the Q prime or Q bar. Okay, so it's not forbidden anymore, which means we can use 1, 1 as input. If you want to understand why it's equal to Q and prime, you can look at this diagram here. Okay, that's the internal logic circuit for the JK flip-flop. Yeah, for the matter of time, I won't do the detailed analysis for this one. You can try by yourself if you are interested. Okay, but most time we will use the flip-flop as a whole, as a module. Okay, so you don't have to worry about that. You just need to understand this symbol and this table. Okay. Again, let's try this using a timing diagram. Let's try to figure out Q. Okay, so Q we mean Q1 plus 1, but you can just put a Q there. Okay, so let's say Q start also start, or we can do something different. Let's say Q start from 1, not 0. Let's see what's good. If we can do that. Okay, Q start at 1 this time. So let's ignore the first edge here, just a start point. So Q start with 1, and because there is no rising edge coming, so keep at 1 until the first or second, as shown here, the second rising edge here. Because J is 1, K is 0. So if we look at the table, so 1, 0 corresponding to set, right? Set means Q will stay at 1 until next edge. At the next edge, we have 0, 1. That's the reset state. So Q will change to 0 here. Then keep 0 until next edge. Then we got 1, 1. 1, 1 means flip. So just flip to, because flip means or toggle. A more official word is called toggle. Just means the value always be different from its previous value. Okay, so because right now it's 0, so at this edge it will change to 1. And at the next edge we got 0, 0, which is no change. So we keep 1. 1, 0, that's set, so it will keep 1. Then we have 0, 0, so no change, it will keep at 1. Then we get 0, 0, still keep. Then we have 0, 1, which is reset, so it will be reset to 0. Last we have 0, 0, so no change. I think the only thing you need to be careful here is we have the toggle state. Okay, when we have JK equal to 1, 1, we have the toggle state. Okay, the last commonly used flip-flop I want to introduce to you is called toggle flip-flop. So in toggle flip-flops, the output kind of toggles between high and low state when there is a clock edge coming and T input is active. Okay, so unit T is active high. So let's try to write the excitation table for this. So we have the clock, have T input, then we have Q, and then we have Q bar. Okay, so if clock is not at rising edge, because we have a rising edge device here, then it doesn't matter what happens to T. qn plus 1 always equal to qn, so no change, right? Now if it's at rising edge, if t equal to 0, 0 is not active, so which means the output still won't change. When we have a rising edge and t is active at that moment, okay, then the q will toggle. So qn plus 1 equal to qn bar, qn plus 1 bar equal to qn. It just toggles the output. Okay, you can realize the t flip-flop using d flip-flop and an XOR gate. Just collect the output back to the input like that. Okay, again, I will leave the analysis to you if you are interested. Okay, so the important thing is that you understand how the t flip-flop works as a module. And we need to add more inputs to the existing flip-flops to have better control over it. Okay, and one type of input we can add is called asynchronous preset and clear. So this can, because if you remember, when we are doing work with the flip-flops, we always have to assume an initial state, right? It looks like we cannot control it, but technically we can by adding some input to the flip-flop or latches. Okay, so one way is to use the asynchronous preset and clear. Asynchronous basically means those input are not controlled like clock, just as the D input. Remember, like when flip-flop work, if we want to use the flip-flop, we have to wait a clock edge coming, so the output can follow the D input, right? But for asynchronous input, they don't have to wait for the clock signal. They basically, you can think they have higher priority than the clock signal. Once they are active, the output will change depending on those values. Okay, like you can overwrite the clock signal. So the excitation table would look like that. So if you notice here in this example, both the preset and the clear input, they are active low. Okay. So if they are both active, actually this cannot happen, because if this value, if we have both of them equal to 0, we try to set and clear the output at the same time. Set means make the output to be 1. Clear means make the output Q to be 0, right? We cannot do this at the same time. So you are trying to avoid this. Don't use that. Okay? Don't set that. But say, hey, I want my initial output to be 1. What do? I just need to activate the preset input while deactivating the clear input. So 0, 1. This will set the initial output to 1. Okay, and if I activate the clear input, I can reset the output, the initial value, to 0. Okay, for the rest, it's the same as the D flip-flop we talked before. Okay. But be careful. To make this happen, you have to set both preset and clear to be deactivated. Okay. In this case, they have to be 1 at the same time. And now, again, let's use the timing diagram to test our understanding on this. So let's try to figure out the Q here. So I have the clock edges at these locations. But in this case, we also need to observe the value of these 2 inputs, right? So let's check. Initially, clear is 0, preset is 1. So if we check this, actually they reset the clear. Maybe we don't call it reset because we have a reset here. So let's call it clear state, right? clear state, then Q has to be 0. And we need to check again at the first edge. So this is still 0, still 1, which means still in clear state. Q has to keep as 0 until the next edge. Okay. Oh no, actually we can't. This is not right. Let me redo this. So here we know it's 0, 1, so it's still reset. So it will reset, but at this moment, actually there's some change in the asynchronous input, so we have to check that. So at this edge, after this change to 1, this change to 1. So 1, 1 means both the inputs are not active. Okay, but there's no rising edge. Then we know that the Q still keep its original value, which is 0 here. Now at the next edge, we got 1, 1. So the inputs are not active. And we have a rising edge. So at this moment, Q need to follow D, and D is 1. So Q will equal to 1. And because these two values are not changing during this period, so the output will also not change. So to the next edge, we still got a 1, 1 here, no problem, but D equal to 0, so Q need to go back to 0. And we need to be careful that at this moment, the asynchronous input changed again. So it changed to 1 and 0. So 1 and 0, now this is what? So preset is 0. So here it's we can call it preset or preset state. So this preset state means Q will equal to 1, even though we don't have a rising edge. As I said, this is asynchronous, so it overwrites the clock. So it still sets the output, and here it changed to 1, 1, so not active. So it will keep the same value until next edge. At the next edge, D equal to 0, so Q has to go back to 0. Okay, so you got the idea. So with the asynchronous input, you need to be aware when those input changes. Okay, because that could change your output, even though there is no clock edge. Finally, I want to talk a little bit more about the difference between latches and flip-flops. Okay, and we already know that in reality, we always prefer flip-flops than the latches. Part of the reason is that the latches has forbidden or no use states, if you remember, but that's not the main reason. There's another very important reason. Okay, that's like any one unwanted change in the input could be passed to the output in the latch, but it won't pass to the output in the flip-flop. How can this happen? Let's see. Say I want to pass a signal, such a signal, to the output of a latch and a flip-flop. Let's see what's the difference. Okay, first we have a perfect signal. So this perfect, so let's assume this is a signal going to the D input for the latch and the flip-flop. Okay, so for the latch, we know the Q wouldn't. I need to add the enable input. So for the latch, we have the enable input, and the unit in order to pass a signal, the enable input should be set like that. So it needs to be active, say before the signal coming. Okay, and when the signal is passed, it will be shut down. Okay, something like that. So if we get an enable input like that, so Q then will be equal to, it will, if the enable is active, the Q will follow D, right? they just follow D like that. Okay. Now for the say for flip-flop. In flip-flop we have the clock signal. So for the clock signal we do things a little bit different. So we want to pass this D. So actually the clock edge should come after the D value change. Okay. So let's just assume the rising edge one. So the Q will equal to, it will change here. Okay. But after that it will follow, it not follow, it just keep it the value if there's no other rising edge coming, right? So this one will pass to the output. Okay, now what happens? Something happens in the input signal. This is kind of normal. Sometimes because of the cosmic radiation or some noise from the environment or from the machine itself, system itself. So the original signal got some glitch. So it should be 1 here, but it changed to 0 somehow, then back to 1. So this is the, here this part is the glitch. Okay. Okay, just somehow the part of the signal changed. Then let's see how these two devices will behave. For the latch, we still have the same enable input. So the Q, because Q will follow D, right? So this error, this glitch, will be copied to your output of your latch. Right? We want perfect signal, but now I got this. However, for FF, as long as the clock rising edge comes before the glitch, so the D will change here. And even though we got the glitch here, but because there is no rising edge, so the Q will not change. So for the first case and the second case, for the flip-flop, with or without the glitch won't affect our output, but it will affect the output in latch. So that's the main advantage for the flip-flop over latch. Okay, so that's why people always prefer to use flip-flop instead of latches. Okay. All right. So this is all about the basic sequential logic circuit. Okay, and yeah, I will talk to you again next time.